Hello ladies and gentlemen, welcome in my first part of atomic matters computation system tutorial, and I would like to show you key features of application, and I'm going to show you how to establish the object of calculations. The main idea of user interface of application basis of system of tabs or bookmarks with hierarchic structure. Such structure is very useful for comparing the set of results between different parameters of calculation. For example, if we open ATMA file, ATMA is the registered extension of atomic matrix computation systems input-output files. So let's just choose an example of results. We can choose, for example, terbium 3 plus ion in terbium 2 iron 17. Okay, after pressing open, we can see 4 set of results, and we can decide which of them we would like to see or not. If we don't change anything, we load whole 4 set of result. Has a 4 major tabs, contain minor tabs when we can find whole parameters and results of calculation for terbium 3 plus ion in solid state matrix defined by crystal electric field surroundings, described by Stevens parameters as follows. The same we can see in other tabs, but because the calculation in the first tab was made in JJZ, we can see only parameters from crystal electric field surroundings, but in last tab contains spin orbit coupling constant and spin orbit coupling interactions. So 1 parameters more will be delivered to this tab. Of course, we can easily compare input tabs from different set of results, but let's look on the result tabs from one of result. On second tab we can see Hamiltonian matrix. Of course, this is a matrix before diagonalization process, and we can see values of matrix elements. This matrix is real in JJZ matrix base. On next tab we can see crystal electric field view. This is very interesting tab. Here we can change many of parameters of visualization when we can view full 3D projection of electrostatic potential defined by parameters shown on the left. Next tab give us energy level scheme, when we can change units of visible levels and scale of projection. Of course, we can see X or Z component of quantum expected numbers of angular momentum, and we can see moments of states and directional and spin and orbit component of magnetic moments of those states. Here you can see many of tools for easy visualization of energy level scheme, and here you can see detailed text information about energy level scheme, eigenvectors, eigenfunctions, and non-zero elements, transition elements between states. Here you can see values of transition elements between states, color intensity informs about proportional intensity of transition between energy levels. On this screen you can see many interesting things for visualization energy levels. In this screen is not very useful, but if we change base of calculation, third major tab give us information about calculation in whole LS, LZ, SZ base. Okay, let's go back to the first tab and let's look on the spectroscopy tab. Spectroscopy tab is the tab for spectroscope simulation. This simulation is made according transition elements shown on this tab. The representation of spectroscopy absorption peaks can be convoluted by Lorentz or Gauss distribution and thermal limitation according to Boltzmann distribution. Temperature simulation and half-width of peaks we can define in this window here and here. After establishing parameters of simulation, we can pressing button and we can see changes in spectra. Next tab allows to see temperature dependence of magnetic susceptibility in various scales and various temperature range in comparison with Curie law. And you can see that magnetic susceptibility along x direction is almost laying on the axis, but when we change value on the vertical scale, you can see that it's really non-zero but very low value of magnetic susceptibility along x directions. Next tab allows us to see inverse of magnetic susceptibility. Of course, we can change the scale. This tab allows to calculate a value of effective magnetic moment according to Curie law. Value of effective moment, it's visible here. Next tab is the specific heat tab. In this tab we can see specific heat distribution curve in the range of temperature. We can establish value of max temperature, and we can compare and add the by curve of a net component of specific heat. Of course, sum of those components is visible, clearly visible as a blue line. Next step is the entropy. Entropy allows us to see values of magnetic entropy distribution in the same range of temperature as specific heat. And the last minor tab is the description, when we can have printed values of parameters one more, and we can add some text information. All those tabs are the results taken from parameters shown in the first tab called parameters. The parameters tab is also starting point for brand new calculations. In this case, you can use transfer parameters button and select cation on using crystal field for transferring it for another ion. You can decide what to do. When you decide to using existing ion, you can changing parameters of crystal field and starting new calculation by using one of these two buttons. This button allows to create new set of results according like 4 of them visible here. This button allows to overwrite one of set of results to changing its contents for another one. After pushing button with creating new results, we can see new results tab called result 9 in this case, of course, but this name can be changed by pressing left button mouse and choosing rename tab, for example, my new result. If you would like to start brand new calculation for another ion with another field, you can choose periodic table, first tab, and choose ion freely. After it, choosing oxidation state, base of calculations, JJZ of lowest multiplet or whole term calculation, type of matrix elements, real or complex, and after it decide to choose values of Stevens parameters. In this screen you can put value of parameters, value of spin orbit coupling, and external magnetic field, and after it, after pressing one of starting button, you can expect calculations of iron 4+ in crystal field defined by parameters written here with spin orbit coupling and under influence of external magnetic field 11 Tesla along Z axis. Thank you very much. This is the first part of our tutorial about atomic matters computation system. Thank you for your patience and sorry for my bad English.